So how do we use PACF and ACF for model selection? PACF is usually used to select the order of an AR model, and ACF is used to select the model of an MA model. And then, yeah, other ways for model selection to do it maybe a bit more automatic is AIC, Archaic Information Criterion, which is defined as here, as shown here. So it is basically the log of the in-sample MSE penalized by the amount of parameters in your model, right? So what it tells you is that the more parameters you have, it gets penalized. The fit gets penalized. Yeah, and this is a method very common in statistics for model selection and for hyperparameter selection. The advantage is obviously that there is no need for an additional validation set or for cross-validation, because you just look at your in-sample fit. Then there is this AICC, which is a bias-corrected version for small amounts of data. And then there are some very interesting theoretical results that the AICC is asymptotically equivalent to a one-step ahead out-of-sample forecast. So basically, by doing AIC, you get the benefits of doing some form of cross-validation, but without doing it. Yeah, a big drawback of the AIC is that it cannot be used across different models and model classes where the parameters are not comparable. Yeah, and so therefore it's usually not used in machine learning, because there, well, we have lots of parameters. The models are not really comparable, and then looking at the fit, yeah, it's not very compatible with the machine learning way of doing things. Yeah, so how would some form of a manual ARIMA workflow then look like? And so this picture is sorry, let me zoom in a bit. Yeah, so this picture, you can find that in the FPP2 book, Rob Hindman's great book. So the way it would look like, you plot your data, identify unusual observations, you understand the patterns. If necessary, you use a box-Cox transformation to stabilize the variance. And then you can use an automated algorithm, which is then just you fit the whole things and you're pretty much done. Or you can do the manual way. So if necessary, you difference the data until it appears stationary. Then you use a unit root test. If you are unsure, you plot ACF, PACF of the difference data and try to determine possible candidate models. You try your chosen models and use AICC to search for a better model. And then you check the residuals from your chosen model by plotting ACF of the residuals. And you can also do this portmanteau test. Yeah. And then if the residuals look like white noise, then you know you have a good model that models all the signal in the data, and everything that is left in the residuals is just white noise. And if not, then you need to go back and iterate. Yeah, exactly. And as I said, there are automatic procedures that kind of automate that, and that's what we're going to look at next. Okay. So there are these automatic functions, ETS and AutoARIMA. There are standard implementations from the forecast package in R. They are also implemented in Fable, which is a tidyverse version, and then obviously Stats Forecast in Python, that is a direct port of these functions from R to Python. So they are all quite equivalent. There are wrappers for automatic model selection of ETS and ARIMA. The ETS function in Python is called AutoETS. It has 15 models with different error, trend, and seasonality. So for example, it has multiplicative and additive error. It has multiplicative, additive damped trend, additive, multiplicative seasonalities. AutoARIMA, it's searched by default up to an order of 5 for both P and Q, so both for the AR and the MA part. And it does up to 2 times differencing. And then you have parameters where you can change that and let it search for bigger model sizes and so on. Then the best model is chosen with AIC, and these are really widely used standard benchmarks, and they are still today quite competitive when it comes to the data where they for which they're actually meant to be used, which is monthly data, quarterly, yearly data. So basically where you have only one seasonality, because these methods do not handle multiple seasonalities. You have one seasonality and the seasonal period is rather short. So for example, monthly data, your seasonal period is 12. Quarterly data, it's 4, because you have 4 quarters in a year. That's the data where these models performed well in the past, and still today they often perform quite well. Yeah, ETS, that's the forecast that we've already seen. As I said, it's not great because the series seems to have some sort of, I don't know, exponential trend, and then this variance here is growing, and the forecast seems to be more like it stays here and keeps the variance the same. So ETS seems to have chosen, you see it has chosen, we can actually read that here, it has chosen a model with multiplicative error, additive damped trend, and multiplicative seasonality, right? So these components are ETS. Yeah, and maybe an additive damped trend is not a smart choice here. So that's just what the AIC told us is best. So, but if we think we know better, then we can just kind of override this and we say, give me please an MMM model. So multiplicative error, multiplicative trend, multiplicative seasonality. We don't want damping. And then the forecast that we get is this one, which models exactly this kind of exponential trend and the multiplicative seasonality. Yeah, similar AutoARIMA, we just run AutoARIMA, and that out of the box directly gives us a forecast that looks a bit more reasonable. So you see, quite decent forecast.